So good morning. My name is Gunjan. I'm a product manager in AI platform software team. Mostly take care of inference solutions at NVIDIA. And today we are going to talk about TensorRT for RTX, which is a new library we just announced at the Build conference, which is dedicated for doing local AI on RTX GPUs. Little bit of background about how GeForce RTX has evolved in the AI space over the last 7 years. It all started when we introduced Tensor cores, specialized hardware, into our GeForce GPUs in order to make AI applications possible in RTX. Now, with that, the market share of the GeForce GPUs has exploded. It's close to 100 million discrete GPU users worldwide, and more than 750 games and apps have adopted RTX and running various AI use cases on them. Starting with what we first introduced was for gamers, DLSS. This is an upsampling solution. It tries to inject frames in between your game rendering. So using AI so that you don't have to package every scene with your app or with your game. Followed on, we introduced AI features for creators and broadcasters, and then later consumers of these broadcasters using SDKs and applications inbuilt within NVIDIA. Our last year introduction was enabling AI use cases in productivity, and then lately, early this year, we started shipping NIMs for RTX GPUs. NIMs, as you might know, are packaged containers with end-to-end AI solution, completely optimized by NVIDIA software stack, in this case TensorRT. So NVIDIA has been accelerating the entire PC AI lifecycle from development to deployment. Starting on the right, for people use PyTorch for rapid experimentation. They train models, they fine tune it, and they would like to run it on the GPU for inference. That's where we accelerate through CUDA. We also have NIM, like pre-packaged optimized engines, which can be used for rapid prototyping. These are run on a PC GPU using the WSL system. So these are Linux models optimized for a Linux system, and it comes with all the tool chain completely in a containerized solution. Under the hood, it uses TensorRT, an inference library for accelerating. Followed on with a developer open source framework like llama.cpp. We offer specialized kernels. We directly work with Llama to introduce optimized kernels written in CUDA. And we also have self-contained NVIDIA AI SDKs. These are ready to use AI features that you can use in apps and games. They are optimized for Windows PCs, and under the hood they are all accelerated by TensorRT library. And lastly, for if you have your own model and if you have your own app, you want to accelerate it using AI, then the Windows ML and TensorRT stack allows you to do that seamlessly. So you have a trained model, you can accelerate that on any of the hardware vendor targets like CPUs, GPUs, NPUs using the Windows ML standardized API. And then whenever you have an RTX GPU in the system, that's when Windows ML delegates the work to TensorRT library, and TensorRT accelerates it for the NVIDIA GPU. So while building apps, today we want to focus on local AI app building challenges. App developers need to meet some really tight latency requirements, and as a result, they have very high compute requirements as well. You have to squeeze the entire run of the AI model within a specific time budget. Like there are use cases taking tens of milliseconds to tens of seconds, right? And if you cram so much of operations, you need really high compute requirements in your machine to be able to do that. Furthermore, there are a variety of hardware and software machines in the market. NVIDIA, although with the discrete GPU, it owns more than 80% of a GPU market share, but there are still so many other CPU and NPU vendors out there and more GPU vendors as well. An app developer has to think about how his or her app can be deployed across this entire ecosystem. Not only from the hardware perspective, but each of the vendors have their own software acceleration libraries as well. So they need to pick a solution that scales. And lastly, if you have a great app, if you have great AI features, you've figured it out how to run it on various pipeline. Finally, when you try to deploy it, you have to really try to make your app fit on the machine. So there are like library size constraints, memory consumption constraints, power, etc. So these are like day-to-day challenges for any local AI ISV app developer. So far, they have been using TensorRT for running inference on NVIDIA GPUs. So apart from RTX, the TensorRT library is able to optimize models trained in any framework on any of our GPU platforms, right? So all the way from data center GPUs to drive platforms and including even an ASIC, which is NVIDIA DLA, right? So models can be trained in any of the framework, and TensorRT makes sure they can run in an optimized fashion.
Sorry, I don't want to break the flow. You said excluding RTX? Everything
Include apart from RTX.
Apart from RTX.
Apart from RTX, yes, yes. All right. So let's take a moment to understand how TensorRT library or inference library works. A developer can have a trained AI model represented in a format like Onyx. The developer can then try to optimize this model, for example, run a quantization operation, try to reduce the weights from 16 bits to 8 bits or 4 bits. After you optimize this model using a quantization library, we offer our own called NVIDIA TensorRT Model Optimizer. The optimized model can be further converted into performant engine, a TensorRT engine, using the TensorRT compiler, right? What it does is it tries to map the layers in the trained model into CUDA kernels that are specialized for the target GPU. So this path requires GPU in the loop. Finally, when an engine is generated, they can be packaged with the application. So developers have been using this and seeing massive performance boost compared to default solutions like DirectML. Some popular apps see more than 50% boost, and in some cases even 100%. So this is the pre-optimization workflow, and however this is known to provide great performance benefits, it comes with its own challenges, and as a result TensorRT has had some challenges with app adoption, where developers don't just care about performance, but like we saw before, they care about workflow simplicity and deployment flexibility as well. In the case of workflow simplicity, TensorRT takes a lot of time for finding the right kernels for the target GPU. So this can end up into a few minutes of compilation or engine building. Moreover, the library footprint was also quite high, making it difficult to ship with the app. And developers that are tuned to developing on Linux cannot directly take their work and port it to Windows. They have to recompile on a Windows OS as well. So there was OS incompatibility between engines. Beyond the OS compatibility, there is also an architecture compatibility limitation. And although a TensorRT engine, when compiled on any of the GPU, can work on rest of the GPUs in the family, but it comes with its own drawbacks in terms of performance, because the GPU that was used in the loop during compilation may not have the information about rest of the GPUs, so it may lose out on utilizing the full tensor core capacity of higher end GPUs to the tune of almost 20% in some cases. And lastly, in terms of deployment, if you have m number of use cases, AI use cases mapped to each individual model. Then for m model and n number of GPUs in your install base, you have to ship a cross product of that many engines that makes your app size larger. So in order to solve these app adoption challenges, we have introduced TensorRT for RTX in this build conference. It's a dedicated library for deploying AI on RTX and RTX Pro GPUs. Right? Instead of pre-compiling engines before, this new library introduces a just-in-time compilation or a JIT compiler, which directly compiles optimized engine on the target GPU in less than 30 seconds. It's easy to integrate because it works as a inference backend in the Windows ML framework for RTX GPUs. So developers only have to call into the Windows ML API, and Windows ML lowers it down to TensorRT under the hood. So developers don't have to worry about directly integrating TensorRT APIs. However, if a developer wants more control, we also offer an independent SDK solution as well. The library is massively reduced in size from 1.5 GB to under 200 megabytes. So we feel this will really make app deployment, integration into app easier because of the smaller footprint. And it works for any RTX GPU that has tensor cores and for a variety of model types. So in terms of using TensorRT for RTX, there are two paths. One is, like we mentioned, through Windows ML. Windows ML gives you the standardized API for taking any trained model and deploying on any of the hardware execution providers. Backends are called execution providers in the Windows ML stack. For NVIDIA GPUs, it's called NVIDIA TensorRT for RTX execution provider. For other vendors, they may have their own. So Windows ML abstracts away the complexity behind downloading the execution provider, calling the right APIs by providing just a standardized API to the application. The model could either be your model or it could be one of the models trained by Microsoft and uploaded to Windows AI Foundry as well. In the standalone path, if a developer wants to use the advanced features of the SDK, for example, call into the Python bindings, which is something not available with the Windows stack, they can directly install the standalone SDK and call its own APIs. The standalone path also gives you advanced control in terms of handling the library while deployed on the app. So the Windows ML preview build with TensorRT RTX is already available starting this week, and then the standalone SDK will be generally available in June on developer.nvidia.com.
So can I just ask?
Sure.
So the Windows ML is that going to work via WSL as well?
This is the native Windows path. Windows ML is for native Windows application.
Okay.
Yeah. Okay. So zooming in a little bit on how the new library works. It's a just-in-time compiler, comes with a two-stage compilation process. In the first step, you take a trained model and you do graph optimizations which are independent of the hardware, and that generates an intermediate engine, a JITable engine, which can also be weightless if you wanted. This is a one-time cost. It takes under 15 to 30 seconds for most of the models, and then the generated engine can be packaged with the applications if you are doing it ahead of time or in an offline phase. Because the time it takes is really small, one can even hide this compilation process directly on the end user device during, for example, time of installation. In the second stage of compilation, which is called just-in-time, this requires the target GPU information. For example, how many SM cores it has, what is the compute capacity, etc. However, this stage is super fast, takes less than 5 seconds for most of the models. And once you have generated the optimized kernels, they are saved in a cache, so that the next time you invoke the AI feature, it's a near instantaneous experience. And by the virtue of having the GPU information, it can now generate dedicated engines for the target GPU, which gives almost 20% perf boost compared to the compatible engines we saw before. If it were a weightless ahead of time engine, and if you are shipping an Onyx model along with the app, it can extract the weights from the Onyx model and embed that along with the kernels generated, so the final executable engine is self-contained and can run. So another level of developer flexibility if they were going to ship Onyx model anyways for other IHV vendors. Here's a quick look at more than 800 models that we compiled with the JIT library. Individually, the AOT stage takes on average less than 15 seconds for most of the models, including even diffusion models to the tune of something like SDXL or Flux. This can be run even on a CPU. It doesn't need a GPU in the loop. And then the time is consistent irrespective of where you have compiled this, right? The model combination included some of NVIDIA's proprietary models and a lot of partner models as well, and also OSS models. On the JITting side, it's even faster, less than 5 seconds for most of the models, less than a second for some of the models we'll see later in the demo. Now, with the kernel information available on the device, the dynamic kernels that are generated that are optimized for the target GPU. Okay. We will also talk how this kernel generation is organic. It starts with a fallback kernel that handles any shape for the model, and then as the user interacts more with the app, it generates faster kernels in the background and replaces it with the fallback kernel behind the scene, so that as you keep using the app, your performance gets better. In terms of performance, as we saw before, TensorRT for RTX continues to have the leverage over DirectML by more than 50%, like its previous library. And compared to the legacy library, it's 8 times smaller and 12 times faster in terms of engine building and comparable perf, right? So starting from first principles, TensorRT has been a performance optimization solution. So keeping or building on top of that performance story, TensorRT for RTX has simplified the deployment pipeline as well. And with the flexibility of all the data types, developer can choose what precision works best for them all the way up to FP4. Once you quantize your model, it gives you the additional performance boost because of less computations and hardware native acceleration offered by the RTX GPUs. For example, on the left we see if we did image generation using state-of-the-art Flux model, 1K by 1K image on a 16-bit pipeline compared to a 4-bit pipeline, there is almost a 3x perf boost, right, without any degradation to the quality. So there is a lot of quantization and accuracy validation that had happened before making the FP4 model checkpoint run on the GPU. All that quantization techniques and accuracy validation are also offered by the TensorRT model optimizer library. The good part of the ecosystem is all the libraries work with each other, so you can choose which one to use instead of taking open source alternatives. In the video generation pipeline, we profiled a 480 pixel LTX video. Compared to Torch's 16-bit pipeline, TensorRT RTX 8-bit pipeline showed more than 2x faster video generation. This is a 7-second video generated in less than 15 seconds on a RTX 5090 GPU. Alright, talking about the advanced features available with the standalone SDK, we spoke about how faster kernels are generated in the background. That is what we call true dynamic shapes. So while the library can generate fallback kernel, the first time it sees a user's shape information, it adapts to the input shape and generates faster kernels in the background. So user can get a quick first click experience, but at the same time from the second click onwards, the performance keeps increasing. The steady state performance is more than 15% compared to the first run. With a configurable cache, developers can choose what kernels to save, when to flush it, how to update it across app update cycles, or even use it, share the cache between apps if required. With the CPU only AOT functionality, it frees up the developer to own so many GPUs in their development environment. Just use the CPU, generate an AOT engine and package it with the app. Or if they want to save even that cost, they can ship the entire end-to-end library under 200 megabytes and incur this AOT latency during app installation, right? Being a one-time cost, it can be hidden during installation or any other background processes. There are dedicated flags to instruct the library how many target GPU architectures should it support. So if you knew your app is only going to work on higher end or for example Blackwell series GPUs, you can instruct the AOT to exclude all the other GPU targets and it will compile even faster. And without the weights in the AOT, it's just tens of kilobytes. So if you happen to ship the AOT engines with the app, it doesn't cause a hole in your application library footprint. We spoke about refitting weights from the Onyx model on the end user device. So this refitting is also a one-time cost. Once you have fitted the weights with the engine, they stick with the engine and you don't have to incur the refitting cost again, which in any case is just a few seconds. Alright, so we were happy to share the early versions of our libraries with some of our partners, and we are amazed by the results it generated. Here is a Topaz Starlight mini feature. What it does is it converts blurry videos into fine, refined videos, all on a desktop GPU, right? It's available in their new application Video AI version 7. Here's a quick demo for the same. So between Torch default implementation and TRT RTX, we see more than 50% boost for 300 frames at 1K resolution. And this is generated on a RTX 6000 workstation GPU. So the library works on both workstation and desktop GPUs. I also want to show a quick demo about how to generate videos within reasonable time using RTX GPU. Okay, so this is a latest LTX video from Lightrix. We are using their 2 billion model. 2 billion is the size of the transformer. We compare the Torch BF16 runtime with TRT RTX's FP16 and then FP8 pipeline. Here in the last pipeline, the FP8 that it says is just the transformer precision, which is the bulk of the pipeline, whereas rest of the components of the diffusion model are still running in FP16. So we'll compare the generation latency of these three pipelines and we'll see the kind of performance boost that is possible on a 5090 GPU.
restart? I think you just restarted the account.
Oh, it's
Oh, there it is.
setting up, yeah. Okay, so this is an image to video use case. We give it a prompt and input image, and it's generating the target video. As you can see, there are 50 diffusion steps. So this is all running on a 5090 Windows machine. So Torch is running in eager mode. Okay, so the time it took is almost 36 seconds, and it generated 161 frames. That's recommended by LTX for a short video, and then the throughput was 4.5 frames per second. Transformer took the most time, close to 34 seconds, and then the rest of the pipeline using the T5 encoder and the VAE encoder decoders are less than 1 second in total. And this is the generated video. Okay, now TRT RTX BF16 pipeline is running. Now between these two contexts, the notebook is offloading the model checkpoints from Torch and reloading them, and also compiling. Okay, so as you can see, the ahead of time engine for this model was already compiled, but the just in time footprint of this is total less than 1 second for all the 4 components. So imagine if a developer is already shipping the AOT engine, the JIT latency on this model is really small. After JITting the engine, when you actually run the engine, it takes another 50 diffusion steps and finishes the video generation in around 22 seconds. So here, as you can see, transformer pipeline is rapidly accelerated because of the graph optimizations the library did and the faster kernels that it generated compared to the Torch default. And then the video quality is exactly the same. In the FP8, FP16 hybrid pipeline, the transformer would be further accelerated because that's the one running in 8-bit, whereas the others are still in 16-bit. And this is a massive model. Although 2B is just the transformer size, the T5 encoder itself is close to 9 GB, and then the VAE encoder decoders have their own size as well. Totally, I believe it takes around 20 plus GB in memory. Okay, so here's the JIT latency. It took some time for JIT compiling the transformer, but still less than 5 seconds. And then for running, it generated the final video in 18 seconds. So almost 2x perf boost compared to the Torch's implementation. This is the image to video pipeline. If this were a text to video, you can eliminate the VAE encoder cost, and it saves you a few more milliseconds, few hundreds of milliseconds. Okay, so all of this running on a 5090 GPU using TensorRT RTX standalone pipeline. Now, in conjunction with the Windows ML pipeline, TRT RTX works as a default backend for RTX GPUs. So since this is available in preview right now, the C++ pipeline, here's a quick illustration of what a developer must do to use this. A trained Onyx model, when deployed along with the app, the app can check the hardware configuration, which system is it running on, and then invoke Windows ML with the hardware info. Windows ML offers a package manager where every IHV vendor has uploaded their inference libraries. So Windows ML downloads and installs the execution provider or the inference backend from the package manager automatically. So imagine an app developer doesn't even have to ship the libraries themselves. Windows ML abstracts away or simplifies the packaging. After the backend library is downloaded and installed, the app can, and this is a one-time process definitely, the app can call into Onyx Runtime compile API. That's another standardized API for compilation, works across all the hardware vendors. In case of NVIDIA and TensorRT RTX, it generates the AOT engine. In the Onyx Runtime lingo, it's also called the EP or Execution Provider Context Model, is just another name for an engine. And after generating the AOT, when you load the engine and start running inference, we incur the JIT cost and start running on the GPU in less than 5 seconds. So this is the workflow a developer can take when trying to integrate through the Windows ML, Onyx Runtime, TRT, RTX pipeline. The C++ APIs are already available, but the Python bindings are still work in progress. However, we hacked around the Python workflow, and we want to show the Python workflow on a Flux model on a 5090. So this is the WinML Onyx Runtime TRT workflow on a Flux model with both FP8 and FP4 precision. So I'll click run. Okay, so when running the FP8 pipeline, as you can see, the sample app is defining what precision to choose for the transformer and for the T5. So it's both FP8 in this case. And then in FP4, the transformer becomes FP4, whereas the T5 still stays in higher precision. Another piece of detail I would like to show here is the selection of the execution provider. So with the Python APIs, you can see you can select the TensorRT RTX execution provider for each of the components of the Flux pipeline. You can choose to run any of this on CPU if required, using the default CPU execution provider. So WinML provides the flexibility how to break down your model onto different hardware. Now running at FP8 precision, this is generating a 1K by 1K image in close to 8 seconds with 30 diffusion steps. Right? We have given it a prompt, it has generated an image. Luckily in this case it's honoring the text syntax. And then when running in FP4 precision using the same prompt and 30 diffusion steps, it generated the image in around 5 seconds. Now here's something I want to show you. We spoke about first run inference versus steady state inference. So in this case, in the FP4 pipeline, it has used fallback kernel for the first run. But if I run the same thing again, there are faster kernels that are generated. Yeah, and that gives you more than 15% perf boost. Now this took less than around 4 seconds to generate the same image. Yeah, so we intend to simplify the diffusion workflows with these true dynamic shapes. It's one of the great features we think is a value add to the diffusion pipelines. And that's why both the video demos or both the demos you can see are diffusion related. So as Gen AI tries to take more and more of the PC AI market, I think we are in a good spot to accelerate that, to do things locally rather than incurring cloud API cost for creators. All right. So to summarize, yeah, we are happy to share TensorRT for RTX both as a standalone library and also integrated through the Windows ML pipeline, keeping to the promise of delivering peak performance more than 50% on direct compared to default implementation like DirectML. It's also easy to use and easy to deploy because of the smaller library size and integration with third-party frameworks. Thank you for listening to me. If you have any questions, I can answer.